Okay, so today we're on to day 2 of geometric sequences and series. A little bit here with a recap from yesterday. Consider infinite geometric sequence where a sub 1 is 4 and r is 1/5. Write the first 5 terms. Well, we'd start up 4. Okay, and then we would go to multiply by 1/5, so 4/5. 4 over 25. 4 over 125, 4 over 625, and we could just keep going if we wanted any more terms. Now, what do we notice about these numbers is it keeps getting smaller and smaller because we keep multiplying by a number less than 1. Okay, so we're going to learn how to sum the first n terms. So if you think about yesterday's formula, okay, yesterday's formula, the sum of n, so in this case n is infinity for us, would be equal to the first term times 1 minus r to the n over 1 minus r. Okay, well, if you think about n here is going to be infinity, well, what's really going on with that? That is 0, right? 1/5 to infinity. 1/5 times 1/5 times 1/5, just getting really, really small. Okay, so in that case, this is actually 4 times 1 minus 0. And that's coming from the idea if we think about the limit as n goes to infinity of 1/5 to the n. So we get really, really small, we can basically become 0 over 4/5. So 1 minus 0 is 1, so it's 4 over 4/5. And then we flip that up to multiply. That is 20 over 4, which is 5. So it might be tough to think about, you have an infinite sequence that actually sums to a whole number. In this case, it sums to 5. Well, really what the equation worked out to be was on top was just 4, which is my first term. So you get your sum of infinite numbers in this sequence is the first term, and the bottom was just your 1 minus r. And this works anytime your r is between -1 and 1. Why does it not work if we have numbers larger than that? Well, let's think about it. If I had numbers larger than 1 or -1, those numbers are going to keep getting bigger. We're not going to sum to anything because those numbers keep getting larger and larger and larger, and they're going to infinity. So let's look at this first example. Okay, so in this first one, we'll see that our first term is 0.9. Okay, and then I just keep multiplying by 0.9, 0.9, 0.9, 0.9 over and over and over. So the sum of the sequence, infinite sequence, would be a sub 1, so 0.9 over 1 minus r, which r is 0.9, which is 0.9 over 0.1, and then this would sum to 9. Okay, so again, an infinite sequence that actually sums to a number. Okay, so each time those numbers are getting smaller and smaller, and eventually they get to almost basically to 0, and that's where we're going to sum right up until 9. Okay, next one, we got to find our first term. So it'll be 2/5 times -1/3 to the 1 minus 1. Oh, 1 minus 1, that's just going to make this be raised to 0, which is just 1. So our first term is 2/5. Sum of... Now, if you notice, as I keep increasing my I in this case, so using I instead of n, as I keep increasing that, we keep multiplying by a -1/3, so r is -1/3, which is between -1 and 1, so we are good. That's 1 minus 1/3, or -1/3, which is 1 plus 1/3. So we end up with 2/5 over 4/3. Multiply by that reciprocal, 6 over 20, or 3/10. So this will actually this infinite sequence, okay, sums to 3/10. That series is going to have a sum of 3/10. Let's talk about another one here. A little bit different. We're not given much of the information there. Okay, so just a reminder, sequence is the numbers being listed out, and then the series is the summing of that. Okay. So the sum of 100 plus 10 plus 1 plus, and we're going to keep going on. Well, obviously we see our first term. Now our r, remember, all we got to do is take a term and divide it by its preceding one. So 10 divided by 100, 1/10 would be our r there, and it is between -1 and 1, so we're good to go. So the sum would be 100 over 1 minus 1/10. 100 divided by 9/10. And then we end up there with a fraction of 1,000 over 9. And we can just leave that as is. Okay, there's your sequence there, the infinite sequence being summed. Anything about 100 plus 10 plus 1 is 111. And then we get to 111.1. And then all that keeps happening is we get another 0.01, then 0.001, 0.0001. And that's what we keep adding to, and we're summing to what comes out to 1,000 over 9, which is 111.11111. Consider this next number. Well, if you actually think about this, I could write this out as 0.3 plus 0.03 plus 0.003, kind of using the idea of what we're doing in that last problem. This 0.01, eventually we keep adding a bunch. Where our first term here would be 0.3, and your r would be 0.03 over 0.3, which is, again, just going to be 1/10. So if we sum this sequence, first term over 1 minus r, okay, get 0.3 over 9/10. If I multiply the reciprocal, 0.3 times 10 is 3, and 3 divided by 9 would sum to 1/3. Well, and that's where we get the idea that 0.3 repeating is the same as 1/3. Oh, you try 0.999, pause it, and then come back and watch the end of it. So consider the same 0.999 repeating, so think about it the same way. 0.9 plus 0.09 plus 0.009. Keep going. Your first term is 0.9. And again, we're going to have that same ratio of 1/10, that common ratio. So 0.9 over 1 minus 1/10. 0.9 over 9/10. Well, think about this. If I multiply the reciprocal, 0.9 times 10 is 9. 9 divided by 9 is 1. And that's how we prove that 0.999 repeating is the... Okay, so now we'll look at some application problems. I'm still using all the formulas that we've learned already to get ourselves through these. So write this first problem. It says write as the quotient of two integers in simplest form. So it wants to take this decimal and basically do what we were doing earlier. Okay, so we could rewrite this as 0.35. Now it's 0.35 repeating, means 353535. So plus 0.0035 plus 0.000035, and that would continue. So easily we see our first term. Our r would be 0.0035 over 0.35, which is 1/100th. Again, if you just need to, you can double check in your calculator on that there. So we can go to what we had yesterday. So 0.35 over 1 minus 1 over 100 using that formula. Now we can write 0.35 as 35 over 100, so we're working with integers over 99 over 100. Multiply by the reciprocal there, and we see that we end up with 35 over 99. Now the nice thing with this, if you have a calculator, and you will with this, you'll see that this works out to be 0.35353535 in your calculator. Now this next one's a little bit different. You'll see that it's 0.4, then the 7 is being repeated. So 7, 7, 7, 7, 7. So we can't write this out exactly how we did before. Okay, so if we think about 0.4 plus 0.07 plus 0.007 plus 0.0007. Okay, it's a little bit different. We got to look at this. This 0.4 is not our first term because there's nothing I'm multiplying that to get to 0.07, the 0.007. So this is really what we need to look at. We need to look at this sequence starting here, where this is my A1, A sub 1. And then R would be 0.07 over 0.007. Okay, so that's going to give you, flip that over. Now, quick way you'll notice you might have an error there is that was not going to work out to be a number that we want. Okay, so we get our 1/10. So let's sum that sequence there. So the first term of 0.07 over 1 minus 1 over 10. We could also write 0.07 as 7 over 100. The bottom here would be 9/10. When I flip that up, okay, that'd be times 10 over 9. So that gives me a 1 there and a 10 there. That gives us 7 over 90. So if you think about that, 7 divided by 90, check, does that give you 0.0777 repeating in your calculator? Yes, it does. What we need to be careful with here is that that's not all we want. We still have this 0.4 out in front. So 0.4 plus 7 over 90, or however you want to go about that. We could change that to be, whichever thing you want to add them there. You can make this be 2/5 plus 7 over 90. You could go to your calculator for that. You don't have to work on really getting the common denominators unless we say no calculator. Okay, and that would work out to be 43 over 90. And again, you can double check, does 43 over 90 give me that fraction, or that decimal, sorry, in my calculator? And yes, it does. Okay. So again, two very similar problems. Just be careful on this one that 4 is not. Okay, we have one more problem here. This one actually has some application to real world stuff here. A ball is dropped from a height of 10 meters and returns to a height of 3/4 of its previous height on each bounce. How far will the ball travel before it comes to rest? Okay, so if we think about this, the ball is being dropped here. It falls down 10 meters, comes back up 3/4 of that, goes back down, comes up 3/4, back down. Again, this is not drawn to scale, just giving you an idea of what's going on here. It eventually comes to rest. So we know our first term of this sequence is 10, right? We start off with 10. It's how far the ball dropped. Okay. Again, we're talking about vertical travel. We're not talking about how far the ball goes out. Okay. Now we know each time it's 3/4. So that's going to be your R. Is this 3/4? So we want to look at what would be the sum of this sequence, where the first term is 10 and R is 3/4. So we end up with 10 over 1/4. Well, 10 divided by 1/4 is 40. And now that would be meters. Okay, but what we got to take into account here is this is just doing one of the directions. It's dropping at 10, then dropping at 3/4 of that, then 3/4, then 3/4. Okay, so we need to take into account the fact that it is going up and down. Okay, so we have 40. Okay, this would be one direction plus 40 of it going the other direction, because if you notice, we double everything here, up and down, 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 the same amount each time. But we would need to take away 10, since this first initial drop does not have a counter action of coming back up that height, which would come out to 70. So this ball traveled a total of 70 meters across